Hello, good evening. Okay, so welcome to our final lecture, okay, for this semester. All right, so for today's lecture, basically we already covered, okay, last week we already covered the concept of virtual memory. Okay, so basically we covered the entire syllabus, okay, for this module. Okay, so today what we're going to do is we're just going to do a quick recap of what we have covered, okay, some of the important things to take note of. The tutorial 5, which covers the scheduling and virtual memory, and I've also uploaded some sort of practice questions, okay, from past year papers. There's a few questions just to give us the idea of the type of questions that have been asked in the past. Okay, so I think we can get started. Okay, so we will start off with the scheduling theory, okay, and virtual memory first. All right, so in this first question here, we are given 3 tasks, okay, T1, T2, and T3. Okay, and for these 3 tasks, we are given the computation time as well as the period. Okay, so the first part A, they ask us what is the utilization. So what is utilization? Utilization is basically the amount of CPU resources we are using. Okay, so to compute that, you take the total amount of computation time per task divided by the period of that task. Okay, and then you sum up everything together. So for task 1, it will be 2 by 6. Okay, for task 2 will be 3 by 8, and for task 3 will be 4 by 15. Okay, so each task utilizes this amount of resources of the CPU. Okay, and then we sum up everything to get the final answer, okay, which is 0.975. All right, so if you look back at our notes, as long as utilization is less than or equal to 1, then it may be schedulable. Okay, may be schedulable. If the utilization is less than the utilization bound, then it is definitely schedulable. All right, so this is a necessary condition. Okay, this is a sufficient condition. Okay, so right now when we do part A, we satisfy the necessary condition. So the bare minimum is fulfilled, but we can't say for sure yet. Okay, if it satisfies the sufficient condition, then we can say for sure that this is schedulable. All right, so in order to confirm whether it can be schedulable, okay, we can check for this criteria. So the utilization bound is computed based on this formula, okay, n 2 to the power of 1 over n minus 1, okay, where n is the number of tasks. Okay, so in our case, n is 3, because you have 3 tasks. So when you compute this, or you just refer back to the table in the notes, okay, you'll get this value. So the utilization bound for n equals to 3, that means 3 tasks is 0.78. Okay, so in our case, 0.975 is greater than 0.78. Okay, so because of this, so this is utilization greater than the utilization bound. So because of this, we are not able to satisfy the sufficient condition. Okay, so necessary condition is satisfied, but sufficient condition is not satisfied. Okay, so if this is not satisfied, then the third way of verifying whether we can actually schedule this is by drawing out the entire sequence for the hyper period. Okay, so what we're going to do is we're going to schedule the tasks, okay, one by one, and we're going to see whether we are able to fulfill the deadline for all the tasks. All right, so if you look at this, basically task 1 has the lowest or the shortest period, so this is the highest priority, followed by task 2, followed by task 3, okay, based on the periodic interval. Okay, so based on RMS, the smaller the period, the higher the priority. So it will be task 1, task 2, task 3. That order we need to execute the task. So at the first instance, when you start Okay. Okay, so what you observe is task 1 will run. Now task 1 takes 2 units. Okay, so maybe okay, so let me put it over here, another copy, so it's easier to see. Okay, so task 1 takes 2 units of time and the period is 6. So you can see that over here, task 1, since all 3 tasks are ready at time t equals to 1, so t1 will run first. Okay, so task 2 and task 3 are all ready. Okay, but because task 1 is higher priority, task 1 will run first, and after task 1 runs, task 2 is able to take over. All right, so when task 2 runs, task 2 will have a computation time of 3 units. Okay, so of course, before we draw this, we also want to take note of the periodic interval of task 1. So the periodic interval of task 1 is 6 units of time. So 1, I start at time t equals to 1 means when t equals to 7 is the next periodic interval of t1. So this one we must take note. Why? Because the moment we hit t equals to 7, the next periodic interval of instance of t1 will kick in, which means that t1 will preempt t2 and t3 at this point of time. Okay, so we just need to take note of that first. Okay, so right now we have taken the first 2 units of time slots for t1. After t1 is complete, we will be able to go on to t2. Okay, so in t2 you take 3 units of time. Okay, and then we also need to take note of the periodic interval of t2. So t2's periodic interval is 8. That means when I start at t equals to 1, at time t equals to 9, the next periodic interval of t2 will kick in. Okay, so now I have completed t1, I completed t2, and I have another 1 unit gap before t1's next instance kicks in. So in that 1 unit of gap, I can actually perform the action for the task t3. So I can compute one of the timing or the compute blocks. So I did 4 timing blocks. So I can use one of it at this point before the T1 kicks in. Okay, so after T1 kicks in, then what happens? Okay, so T1 again takes 2 units of time. Okay, so T1 comes back here, takes 2 units of time. And just nice, when T1 finishes, the next instance of T2 kicks in. So because the next instance of T2 kicks in at time t equals to 9, T2 will take another 3 units. Okay. So then we can go back to having a slot for T1, T3. So you can see that T3 only has 1 unit of time spare to compute. Why? Because T1's interval is 6 units. So after 7, after t equals to 7, the next time it will be repeating is 6 units away, which is at 13. Okay, so which means that I only have 1 time unit at t equals to 12 to compute for t3 before I start t1 again. Okay, so for t2 the next interval is later. Okay, but what happens is once I finish t1, I have 1 more. I don't have t2, so I can go back to t3. But when I do t3, what happens? Okay, I compute 1 more unit of t3. Okay, but if you look at t3, I need a total of 4 units of time that has to be completed by 15 units from the time you release the instance of the task. So I release the instance over here, but at time t equals to 15, I've only completed 3 units of t3. I've not been able to complete all 4 units of t3. Okay, so with this, you can conclude that this task set is not schedulable. Okay, it's not schedulable because you can analyze the timing sequence to see that this task set or task 3 would miss the deadline of 15 to finish its computation requirement of 4 units. Okay, so basically it's always the same process. So the first step is always we start with the utilization. We confirm that the utilization is less than or equal to 1. So that confirms, or that ensures that we fulfill the necessary condition. And we then go on to check whether it fulfills the utilization bound. If it satisfies the utilization bound, then we say it is sufficient. So we don't need to check anything else. Okay, if we satisfy the utilization bound, then we can straight away say it is schedulable. Okay, but in this case, it does not satisfy. Okay, but from what we have learned from the material so far, the notes, we know that even if I don't satisfy utilization bound, I may still be schedulable. Okay, so the way to analyze that is looking at the timing analysis over one hyper period, which is the third step here. So we take note of the priorities assigned to the various tasks, okay, and then we draw out the blocks, okay, timing blocks, to see whether any of the tasks miss the deadline. Okay, if they don't miss the deadline, then it's fine. Okay, but in our case, we can see that task 3 misses the deadline, so it is not schedulable. Okay, so this is just the question, all right, from the scheduling theory to give us a recap on all these different concepts. Okay, on the utilization bound, and the schedulability analysis. Okay, so with that we can conclude that since P3 missed the deadline, we say that this task set is not schedulable. Okay, so that is the final conclusion, okay, based on what we have seen. Okay, so let's go on to the next question, okay, on the virtual memory. Okay, so in this question, it's just again another example to sort of recap what we covered on the virtual memory. So what's the whole idea of virtual memory? Okay, basically we want to be able to hold or access a lot of information, okay, a lot of pages in memory, okay, but the actual memory that you have in a system is limited, okay, whereas you have so many applications that we want to run. All right, so we want to create a form of mapping to allow a process to map its own virtual space to the actual physical space of the memory. All right, so that is the idea of the whole virtual memory system. So in this virtual memory concept, what you need to know is how many bits we have for the virtual address, okay, how many bits we have for the physical address, and what is the size of each page. Okay, so here we are given that we have a virtual memory system with 64 bytes per page, 10-bit virtual address and 9-bit physical address. Okay, so the first question here, part A, what is the maximum size in bytes of the virtual memory? Okay, maximum size in bytes of the virtual memory. So to compute that, okay, you go to 2 to the power of 10 because it is 10 bits. Okay, so you have 1024. Okay, and then the 9-bit physical address. Okay, so for the 9-bit physical address, you have 2 to the power of 9, okay, which is 512. Okay, that is what we have here. So we have 1024 bytes for virtual memory and 512 bytes of physical memory. Okay, that means that is the amount of virtual memory. So in terms of virtual memory, you have more space compared to the physical memory. Okay, and what we want is we want to be able to make sure that whenever we access any virtual memory, we know exactly which page we are referring to and so on. Okay, so in order to do the mapping, they must both have the same page size, which is 64 bytes per page. Okay, so since both of them have the same page size, we can now know how many pages there are going to be over here. Okay, so how do we do this? So 64 bytes. So since I have 64 bytes per page, that means this page here, each page is accessible through 64 bytes, the size. Okay. So for 64 bytes, I need how many bits? So it is 2 to the power of 6. All right. So basically, if you look at the address mapping, what we are saying is I need a total of 6 bits for the page offset. Okay, that means within the page which particular byte I'm referring to. And since both virtual memory and physical memory have the same page size, so if this is virtual memory, the physical memory will also have the same number of bits for the page offset. Okay, which is 6. All right. So this for the virtual memory, this is the physical memory. So if the number of bits for the page offset is the same, then what is remaining will tell us the maximum number of pages available. So for virtual memory, total is 10 bits. And out of the 10 bits, 6 bits is already used for the page offset. So remaining is 4 bits. Okay, so this is for the virtual pages. And here will be 3 for the physical pages. Okay, so what is the maximum number of virtual pages and physical pages? So since I have 4 bits for virtual page, it will be 2 to the power of 4, which is 16 pages. And over here I have 2 to the power of 3, which is 8 pages. Okay, so this is very similar. Okay, if you refer back to our notes, there's the same steps we did. Okay, so if you are not sure, you can always refer back to the notes. The same process, the same steps, okay, that we covered in the lecture is what we're doing here. All right. So once we know this, we can say that okay, we have total of 16 pages in the virtual memory space and 8 pages in the physical space. All right. So with that, okay, you will be able to map virtual addresses to physical addresses. So how do I map this? Okay, so to do the mapping, you need the page table entries. All right, the page table entries to tell us whether the valid bit is set and the mapping of the physical page to the physical, so virtual page to the physical page. So if I look at this page table, okay, you can see that for those entries where the valid bit is set, there is a PPN number, that means the physical page number. Okay, so how do I go about doing the translation? Okay, so let's look at the first one. So the first one is address 0. Okay, that is the virtual address 0. So if I say virtual address 0, what do I get? Okay, so the virtual address 0 is, if I look at the full 10 bits, 0, 0, 0, 0, 0. Okay, so this is the virtual address. Okay, and I want it to map to the physical address. Okay, so to do that, what I need to do is I need to extract out the bits that tell me which virtual page I'm referring to. Okay, so for the virtual address, the upper 4 bits tell me the virtual page I'm referring to. So what I need to do is I need to extract out the upper 4 bits. So this upper 4 bits is 0, 0, 0, 0 means I am pointing to page table entry 0, which is this. Okay, I'm pointing to page table entry 0. And what I do, I extract out the physical page number that maps to that virtual page table entry. So the physical page number is 2. Okay, is 2. That means that value is 0, 1, 0. Okay, that is the physical page, which is this. Okay, physical page. And to complete the physical page, I need the remaining 6 bits. This remaining 6 bits is the same page offset as per your virtual memory. Okay, so this is the physical address. Okay, so that is how you do the mapping from the virtual address to the physical address. Okay, so you can see here. All right, so basically what you have done is you have taken the first 4 bits to map to the line in the table entry, and then from there you take the value in the table and use that to form the upper bits of the actual physical address, and the lower bits are the same as the actual ones in the virtual address. Okay, so it is the same process for all the values. Okay, so maybe we try one more. Okay, then you get the idea. So let's look at this 576. Okay, so 576, you get this. Okay, so this one, of course, you can use your calculator. Okay, so you don't need to use a calculator because you need to know the binary representation. Correct. So let's look at the calculator here. So 576. Okay, so that is the value over here. If you look at the binary value, okay, 1 0 0 1 0 0 0 0 0 0. Okay, so first we convert it to the binary equivalent. Okay, so if I take this entry here, 576, so the binary equivalent is 1 0 0 1 0 0 0 0 0 0. Okay, so that is the binary equivalent. And then since we know that upper 4 bits is referring to the page table entry and the lower 6 bits is referring to the page offset. So this 100 means I look at page table entry 9. So if I look at page table entry 9 over here, I see a value of 6. So the 6 is the value that I will take, okay, to populate here. So that will be 110. Okay, and then from there I can put the other 6 bits, which is all zeros. Okay, and that is your final physical address. Okay, so it is the same process. Okay, so all the addresses, you just follow the same process to get the mapping of the virtual address to the physical address. Okay, so yeah, so those are the questions for the tutorial. Does anybody have any questions that you want to ask?
Sorry, do you mind going through one more example for the last question?
Okay, okay, we can try the last number here.
Thank you.
Okay, 987. So again, what we do 987. So 987. Okay, so in terms of binary, we get this. Okay, so 1111 011 011. Okay, so we can do that. So 1111 011 011. Okay, so that is your virtual address 987. So what we do, we take the so we already know the lower 6 bits is the byte offset, and the upper 4 bits is the pointing to the page table entry. So 1111 means it is 15. Okay, 1111 is 15. So I need to go to the page table entry 15. So in page table entry 15, which is this, I get a value of 1. Okay, the physical address 1. So that 1 is the value that I need to put for the upper 3 bits here. Okay, for the physical address, and this lower 6 bits will get copied over as the same. So it'll be 0, 1, 1, 0, 1, 1. So that is the actual physical address. Okay, so there is a question. So for the mapping, okay, so you need to do the mapping. Okay, for RMS, when you do the mapping, is up to the what we call the hyper period. Okay, so you need to draw out until the hyper period. But if before you reach the hyper period, you already see that any of the tasks miss the deadline, then you don't need to carry on. Okay, so the critical instance analysis, when do we use it? Critical instance analysis is actually the same as drawing out this timing sequence for the hyper period. Okay, so critical instance analysis will give you the same result as drawing out. Okay, the only thing is if you use the critical instance analysis, you are sort of calculating the sort of demand and available resources at each interval. Okay, and as long as you see that it meets at any point of time before the deadline of the task, then you say it is schedulable. Okay, which is the same thing we are doing over here. All right, so it's just two different ways of doing the same thing. So if I were to do the critical instance analysis, I will also be able to get to the same conclusion that it is not schedulable.
So if the hyper or whatever is like 15, 16, if it's 18, then it's schedulable. Is that right?
Yeah, if within the hyper period you do not miss any deadline, then it's schedulable.
Okay. So if it's 18, it's schedulable.
Yeah.
Okay.
Okay, when we use EDF, okay, so the question is if when we use EDF, is it always schedulable? For EDF, okay, as long as your utilization is less than or equal to 1, it is always schedulable. Okay, as long as your utilization is less than or equal to 1 for EDF, it is always schedulable. So you don't need to do any utilization bound or any other check. Okay, as long as you can satisfy this condition, then you say it's always schedulable. Okay, any other questions? Yeah, so in the question is, yeah, when the physical address, your answer for the physical address should be based on the number of bits for the physical address. So in our case, since the physical address is 9 bits, okay, so we represent it in 9 bits. Okay, so let's move on first. If you have questions, you can come back to it later. All right, so let me go over to the so that sort of wraps up all the content. Okay, yeah, so as I said before, this module is the 2 parts, right? The first part is the processor architecture, and this the second half is on the OS and all. Okay, so in all likelihood, the first half is something that you may not see or hear again at all, you know, in the rest of this module. I mean, the rest of this your degree program. Okay, again, that is because it is just something that is we feel that all CS students should know, correct, as part of understanding what is going on at the lowest level of the system. Okay, but I think most of the time you will probably be designing and coding at a much higher level, correct? So unless you really go into low-level hardware design and things like that, then you come back to those process architecture. Okay, if not, you probably don't see it. Okay, but I believe that with that understanding and with the knowledge, you will be able to better appreciate and relate to discussions on hardware selection and sort of discussions that you may come across, right? So in your work or next time you're working on a project and people start discussing about why they chose this processor or why they chose this architecture or things like that, then you can relate it back to understand that yeah, it does play a part. So even though you may be coding at a very high level, okay, but the lower level architecture, the design does play a part in how efficiently your system can work. And also, yeah, so that's the objective. This OS part, yeah, you may come across it in other modules that you may see the concepts, multi-threading and things like that. Okay, so the concepts of multi-threading and how semaphores, mutex work, message queues, every OS has their own sort of syntax, own implementation. Even the way some of this may be implemented could be a bit different. Okay, so whenever you deal with a new OS in the future, just be mindful to have a look through the documentation to understand how it is implemented in that particular OS. Okay, like a simple example I can tell you is, in our case, when you create tasks of equal priority, okay, when a task is running, okay, if I create 2 tasks, okay, in our microC OS environment, okay, if I create T1 and T2, okay, if both of them have the same priority, okay, so I say this is high priority, this is high priority, and if task 1 is running, task 1 will run as long as it wants to run until it goes to a block state or it gives up the CPU. Then only I can transition to task 2, because that is how microC OS is implemented. Okay, if 2 tasks are equal priority, whichever task is currently running will still hold on to the CPU until it gives up the CPU. Okay, but if you try another OS, maybe that behavior may not be how you expect. Correct? Maybe for equal priority tasks, okay, there is actually a constant round robin switching that is going on in the back end. Okay, so even though it is equal priority and one task is running, but the OS may allow other equal priority tasks to also run at the same time since they are considered equal priority. Okay, so these are some of the sort of small things that may be different from one OS to another OS. Okay, it all depends on how it has been designed. Okay, so just be mindful of that when you in your work or in future when you work on other projects. Okay, if you integrate the OS, it's always good to have a read through the details of how some of these things are implemented, so you understand. Okay, and then when you design your architecture, you know how to relate to it. Okay, so let's move on to the exam review questions. So I picked out some questions from the past year paper. Okay, so let's go through them. Okay, so the first question here, okay, so it's ready on Luminous. I uploaded, so I think the weekend I uploaded, so you should be able to see this. So you're asked to examine the code. Okay, so we're given a code. Okay, so this is the code. Okay, so before we go into the code, let's look at what is the information given. Okay, so we are told that task A is created first, followed by task B. Okay, there are no other tasks or interrupts in the system. The main function, okay, has already created a semaphore and initialize it to a value of 1. Okay, so you already have a semaphore with initial value 1. Then you also have a global integer variable counter initialized to a value of 0. And you have another global integer variable init initialized to a value of 1. And we told that task A is a higher priority than task B. Okay, so the first question, which of the printf messages, task A or task B, will be printed out? Okay, so let's look at the code. Okay, so the first thing we know is since task A is higher priority than task B, okay, task A will run first. All right, so that is the first thing that we must understand. So if I were to draw out the timing diagram, so this is task A, okay, this is task B. Okay, so task A will run first. Okay, but when task A runs, okay, if you look here, the first thing that I do is actually I call a delay. Okay, I call a delay. So when I call a delay, what happens? I go to a block state. Okay, so since I go to a block state, I will allow a context switch to task B. So until this point of time, okay, until this point, task B was in the ready state. Okay, it cannot run because a higher priority task is running. Okay, but at the moment task A, I call delay, I allow a context switch so task B can run. Okay, so that is the first thing that we must see. Okay, and since I switch over to task B, I come here and then I execute this code. So init is originally having a value of 1. Correct, init is having a value of 1, which means that when I come to task B, this if condition is true, so I will print out task B. All right, so the first thing that I will do is I will print out task B. Okay, and then I set init to 0. So subsequently, I will not do this printf anymore. Okay, I will not do this printf anymore. So then after that, I just check. I take a semaphore. Okay, I check whether counter is equals to 5. If it's 5, I reset it to 0. Then I release a semaphore. Okay, and then I go back to the loop. So I will basically be going through this while loop, okay, until the delay time expires. Okay, so I'll be going through the while loop, okay, until the delay time expires. So when the delay time expires, what happens? I will switch back here. So this task will be preempted. So over here, I'll get preempted. So I'll go back to a ready state. Okay, and when I come back here to task A, okay, that means I finish the delay, I will check for init. But what happened is when task B printed out, I also set init to 0. Correct. So since init is already 0, this will not happen. So this will not happen. All right. So that is the first part. Okay. So the question asks whether task A or task B will print it out. Okay. So the correct answer is task B will print it out. Okay. And they ask you to explain the answer. So when they say explain, you need to sort of give an explanation of what happens. Correct. So the explanation is, okay, task A gets to run first, but then it goes into a delay or block state, which will allow task B to run. Okay, and the init value, okay, of 1 will allow the if, okay, to be printed. I mean the if to be true, if check to be true. So the printf for task B will be executed. Okay, and since after that init is set to 0, the following if check in both the tasks will be false. So there's no other printer after that. Okay, so that is how you must answer. Okay, so if you never ask for explanation, if the question is what is printed out, task A or task B, then you just say task A or task B. Okay, if there's a thing that say explain the answer, then you need to explain from the execution sequence of the code. Okay, why do you feel it's task A or task B? Okay, so does anybody have any questions about this? Anything you're not sure of why we get the answer as task B? Okay, so in the next part here, part 2, use a state transition diagram to clearly show the changes in the state of both task A and task B. Okay, so that is basically something like this. Okay, so you need to draw out something like this where you can say that at which point you have a context switch. So I think the important thing here is, okay, you must be able to show when the context switch happens. So in our task A, okay, we have the context switch because we call the delay. Okay, then when the delay expire, okay, then we come back to task A. All right, subsequently what happened? Okay, so if you look back at the code, subsequently what happens is task A and task B are just focused on the counter variable. Okay, so what happened is I will take the semaphore. Okay, so the semaphore is used as a way of controlling access to the counter variable. Okay, so whenever I take the semaphore, I will increment the counter variable, okay, in the task A, and then if the counter value is greater than 6, then it will jump to 10. Okay, then I will, so regardless of that, I will do a printf. Okay, so first I increment, do the if check, and do a printf, and then I release the semaphore. Okay, so I'll keep, so every time I do this and I go back to the loop, what happened? Whenever I go back to the loop, the first thing I do is I do the delay. And whenever I do a delay, what happens? I allow task B to run. Okay, so when I come back to task A, okay, what happened is I will increment the counter, do the if check, and then I go back to the delay. Okay, and every time I do a delay, I allow my task B to run. So until then it is ready. And every time I do a delay, I allow task B to run. So when I go to task B, what happens? Okay, so the sequence is again from here to here only because the init is already 0. So I don't need to worry about that. So here to here, what I do? I just take the semaphore, I check if it's equals to 5, then I reset it. Then that's it. Okay, so basically over here, I only do two things. I take a semaphore. So here also you have the semaphore. Okay, so to be more clear, You still have one more block here, which is the SAM pen. Okay, and then the SAM post. Okay, so you still have the SAM pen and SAM post. So the same thing you do over here. You take the SAM, you take the semaphore. Okay, you do the if check. Okay, if counter equal to 5, and then you do the SAM post. Okay, so of course this will keep on running, right? This will keep on running, okay, until when? Until the delay expires. Okay, so maybe I should change the order here. Okay, because I do the SAM post first, followed by the delay. Okay, so I will be continuously doing that until the delay expires. So the delay expire, again, I repeat the whole process. I come back, I take a semaphore, increase counter, and do the whole thing. So your timing sequence should be something like this. Okay, so of course, you can just, once you draw one sequence and you know that it's going to repeat, you can just put a note there that says repeat. Okay, and repeat, something like that. Okay, so this sort of is how you should answer the part 2. That means the timing sequence between the two tasks. Okay, and then the last part is describe how the value held in the counter variable will vary over time. All right, so basically you can see that my counter variable is initialized with 0. Okay, initialized with 0. That means the very first time you become from 0, it will become 1. So I'll print out a 1. Correct. So over in task B, there is no printout. It just checks for 5 only. Then it goes back to 0. All right. So every time it goes to 1, then I go to task B. Nothing happened. Then I go to 2, I print out 2. Okay. Then nothing happened. Then I go to 3, I print out 3. Again, nothing happened. Then I go to 4, I print out 4. Again, nothing happened. When I go to 5, I print out 5. But the moment I print out 5 here, and I pause and I go back to the delay, what happens? At that iteration, when task B gets a chance to run, this condition will be true, which means I will reset it back to 0. Okay, so once I reset it back to 0, then when I go back to the next iteration of task A, okay, I am starting back again over here. So I will increment first to 1, and then I will start again 1 and 2 and so on. Okay, so the printout sequence will be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and so on. Okay, so that will be the way the sequence will change.
Sorry, I find this question quite scary. Cause center will become 0, then it will become 1. The question is not asking what's printer, it's asking how the value will change over time. So it does go to 0 actually.
Correct, correct. So even if you put that it goes to 0 and the sequence is there, it's also correct.
Yeah, okay, thanks.
Okay, so if you had answered that it goes to 0 and then task A resets it back, okay, and then the sequence start, is also considered correct. Okay, any other questions about this? Okay, so this is something like you can expect. Okay, that means you will be given some code. Okay, then you are supposed to analyze the code and then answer some questions regarding the code. Like what will be printed out, what what will happen, what will the variable value or things like that. Okay, so as long as you understand your OS code, okay, which you have also been working on in the assignment and so on, then I think it shouldn't be any issue. Okay, so let me move on first. All right, if you have questions, we'll come back again. Okay. Okay, so in question 2 over here is also another code analysis question. All right, so here we are given 2 tasks. Okay, task 1 is higher priority than task 2. Okay, there's a button press function which will return a logical 1 when the button is pressed. Okay, so OS task queue post, OS task queue pen, and OS time relay here are simplified versions. Okay, so in the exam, okay, because the actual syntax of all of these OS kernel calls is quite long, correct? So to make it easier and more readable, I will usually put a simplified version of it. Okay, but the meaning and the understanding is the same. Okay, so for example here, when you say task queue post, there are actually a lot of other parameters. All right, but the idea is the same. That means when I say task queue post, I'm posting it to a particular task. In this case, task 2, and I'm posting a message. Yeah, so the idea is the same. Okay, so let's look at the code first. So what's the first question? They ask, how will the code execute and the expected outcome? Okay, so since task 1 is a higher priority than task 2, task 1 will run first. So when task 1 runs, okay, this is the while loop, correct? So the first thing is I go to this while loop. Okay, when button press equals to 0. Okay, so as long as button is press return to 0, I'll be stuck in this while loop. Okay, and earlier on explanation is button press function will return a 1 when the physical button is pressed. So if the button is not pressed, I will be stuck here. Correct. So that is the first thing you should understand. Okay, so you are stuck here if button is not pressed. Okay, you're stuck in that line if button is not pressed. Okay, but the moment the button is pressed, I go on to the next line, which is to populate a message and then post the message to task 2. And after that, I do a delay. Okay, so why I do a delay? So this is to allow a context switch. Because once I go to a delay, I block myself, which means that I will allow task 2 to run. And when task 2 runs, what will it do? Task 2 is the first thing that it does is it calls task queue pen to receive a message. And since task 1 already posts the message, so I already post the message here, which means that when task 2 runs and calls task queue pen, it will be able to immediately retrieve the message. Correct? It won't go to a block state. You will be able to immediately retrieve the message and then do some data processing. Okay, so that is the idea. Okay, task 1 is waiting for a button to be pressed. When a button is pressed, it will formulate a message and send it over to task 2. Task 2 will receive that message and do some other processing after that. Okay, so that is the sort of sequence, okay, that we can understand from the code. Okay, so now the next thing is suggest a means of improving the efficiency of the code to allow the multitasking system to fully utilize the CPU's resources. Okay, so basically this question suggests that when you say improve the efficiency, you must look at what is currently inefficient in the way it is processed. Okay, or the way it is written. So the inefficient part is this. Okay, and why is this inefficient? Because the whole idea of multitasking is you want to be able to utilize the CPU to run all your multiple tasks, correct? But here you have a situation where higher priority task is just stuck there because the button is not pressed, and then no other task can do anything. Okay, so as long as you understand that, all right, and you give some explanation based on that, then it is fine. Okay, so if you look at the answer here, what is written is, okay, since task 1 has a higher priority, it will run first. Okay, so when the button press is 0, it will be stuck. So while the button press is 0, that means you have not pressed the button, it will be stuck there. Okay, so the key idea is you will be, task 1 will be sort of hogging the CPU indefinitely, okay, until somebody presses the button, okay, which is the inefficient part, okay, of the whole design that we have. Okay, so in this part, the last part of the question, modify the code to show the improvements. Okay, so the improvement is what can we do to make it better, correct? So that I do not hog the CPU. Okay, I mean, it is up to I mean, you may have different ideas. Okay, one possible solution is this. All right, that means if the button press is still 0, I do a delay. Okay, so instead of being in a loop, okay, I just call a delay as long as I see the button is not pressed. And why this is better in a sense is that since I call a delay, I allow myself to be blocked, which means some other task can run. Okay, so that is one way in which you can make this better. All right, that means you do not allow task 1 to hog the CPU, you allow it to, or you ensure that it gives up the CPU if that particular event doesn't happen. Okay, so even if the button is never pressed at all, you can still be sure the other tasks will have time to execute. Okay, because of that delay there. Okay, so that is another sort of past year question. That means you look at the code, analyze it. Again, you understand it first, correct? What is happening? What is the sequence? And then from there, you look at what are the changes you need to make, okay, to either have some functionality or make it better or things like that. Okay, so does anybody have any questions regarding this? Okay, so let me move on to the next question. Okay, so here we are told that assume A is a local integer variable already declared at the start of a function, and consider the following C code line within the function. So A plus equals to 10. So the question is this considered atomic? So what is atomic? Atomic basically means it can be completed without preemption. Okay, can this line be completed without any preemption? So the answer is no, correct? We already seen this in our lecture slides. So this is equal to A equals to A plus 10, correct? And this is not atomic. Why? Because A is referring to a memory location, correct? A data stored in some memory location. So in order for me to compute this, I need to do a load. Then I need to do the add. Okay, and after I get the result, I need to do a stop. So it is equivalent to at least 3 lines of code in assembly language. Okay, which means that it is possible to be preempted, okay, in the middle of this operation. Okay, so that is the answer for this. Okay, so I think that one, it should be quite straightforward, okay, as long as you understand what is atomic. Okay, part B, is the function, you're given a function here, and is the function here re-entrant? Okay, so what is re-entrant? Re-entrant is basically the concept of having a shared code between different tasks. Right, so if I have task A and I have task B, and both of them need to call this common function here called compute square. Okay, both of them need to call this. Is there an issue? Okay, so the issue, there will be no issue, okay, as long as the function, the shared function, works based on its own automatic or local variables. So when you say automatic or local variable, means the variables that it gets when you pass values to that function and values that it creates on its own stack. Okay, that means if I declare any local variables here, it's fine. Okay, as long as I do not create any static. So I'm not allowed to use any static variables, and I cannot use any global variables. Why? Because if I have any static or global variables, then those values will be retained after I exit the function. Which means that if task A gets preempted by task B, while it was in the midst of this shared function, then task B will end up with values that were used previously by task A and so on. Okay, then the whole thing gets corrupted. Okay, so as long as you do not have any static or global variables, okay, then you are fine. Okay, so in our case, this function is only based on values that are passed to it. You compute and you return back. You do not create any global or static variables, or you do not use any local static variables. So in that case, this is a re-entrant function. That means it's considered thread safe. Okay, so that is also from our discussion in the lecture. Okay, atomic and re-entrant. Yeah, so these are some of the examples of the questions. Okay, I mean, I didn't want to go through too many, but I think this sort of gives you the idea. So there will be some questions that are like this, where is, I would say, theory related. That means concepts that we covered in class. All right. So as long as you remember those concepts, I mean, it's open book, so you can still refer back, okay, and look at it if you, as long as you know where to find it. All right. If you're not, if you look at a question and you've never seen the word before, then it's very difficult. All right. But if you sort of remember where you, which topic, where it was, then it's easy to refer back and try to figure out what to answer. Okay, then in terms of coding, I think as long as you understand those coding examples that you have gone through in class and your assignment and things like that, then I think you're fine. Okay, so that sort of wraps up everything. Okay, like I said, this is the last lecture. We're not having any lecture next week. Okay, wait. Can I change code to? Yeah, I mean, you can change. Yeah, so there's a question of some other alternate solution for this part over here, the code improvement. So this is not a fixed answer. Okay, this is just one possible answer. You can always come up with other solutions. Correct. So one other possible solution is, if the button is pressed, then I go and do this. Correct. So if instead of equal to 0, I say if it's equal to 1, okay, then I go and do this whole thing, this whole chunk over here. Okay, it is also possible. Okay, so there is no fixed answer for this kind of question, but because you are expected to suggest an improvement and encode it. Okay, so in this kind of question, as long as you provide the code, okay, and you put some. Usually, this kind of question is also good to give some comments, okay, to explain what is your idea, correct? Why you think that this is a valid solution. Then it's easy for me to understand your thought process. Okay, so next semester, okay, I think most likely it will be face to face already, you know. I mean, from what I believe only, okay, officially we still have to wait for the university's announcement, okay, but considering that we are already quite open already, you know, in terms of the class sizes and social distancing and things like that, I would, unless something really bad happens lah, okay, in the next 2 to 3 months. If not, I would think that we are going more and more in the direction of face-to-face classes already. Okay, but again, this is just based on my assessment of the current situation. Okay, but officially, I think we still have to wait for NUS to give us the announcement. Okay, for now, if you look at the latest circular, quite a lot of things are already allowed. Okay, in terms of class sizes, also we are allowed bigger class sizes. Okay, so I'm not sure to what extent it will grow or be relaxed further over the next few weeks. Okay, so yeah, so what I will do is, okay, so that's what we have. All right, so for the exam, as I mentioned, it is face to face, open book. Okay, so just make sure you check the luminous or your exam timetable. Okay, let me just, yeah, you should be able to see the exam schedule and timetable from the luminous or from registrar's email. Okay, so just make sure you follow that and show up for the exam, and also check the venue. Most likely it should be the MPSH, okay, the sports hall. Yeah, but anyway, just check the venue again just to be sure. Okay, even MPSH got a few different halls there, right? So just be sure, come earlier, okay, so that you have time to walk around and you know where to wait. Okay, other than that, it's open book. Okay, so open book means you bring in all that you need to bring in. Okay, you must also bring in your MIPS instruction set. Okay, so remember to bring that as well. Okay, because there will be some MIPS assembly language questions that you need to answer as well. All right. Other than that, yeah, your calculator you must remember to bring. Okay. Yeah. Let me see anything else. Yeah. I mean, I will send an announcement closer to the date just to remind you all. But just take note of all these things. Okay. Can I suggest online? Okay. I mean, this is beyond any individual person's suggestion. All right. So once I think they decide to go towards face to face, it will be a bit more or less everybody will follow. Okay, assignment 2 can extend to Sunday. Okay, we can do that. Okay, let me. Okay, let me see where do I. Okay, so does anybody have any other questions? Okay, those who have questions, you can continue to stay. Okay, and I will address those questions. If not, thank you very much. Okay, I will see you all in the exam hall. Okay, if you have things along the way, you can always free to message me or email me. Okay, but just take note that it will take longer for my response, because usually the end of the semester is where I'm flooded with too many emails and too many messages as well. Okay, so it will take a bit longer maybe to reply to you all. Okay, but I will definitely reply. Okay, so thank you very much. Okay, I will still stay on the Zoom call for questions. Okay, if you have no questions, you are free to log off. Okay, calculator, there is no restriction. You can bring any calculator you like. For the assignments, yeah, as long as the uh, output is correct is one, but you must also make sure that you have followed the like minimum number of tasks and the sequence of uh, the way the different tasks execute, then you will get the marks. Correct. If the output is correct, but you did everything in one task, then it doesn't fulfill the purpose. Okay, so you need to make sure that the sequence and the number of tasks, all of that is as per the requirements laid out. Yeah, all the grades and the marking I will be updating this week and next week. Okay, exam tips in particular, I don't have anything except like whatever I went through today, that gives you an idea of some of the type of questions that you can expect to see. Right, that means analysis of code, uh, providing some your own code, you know, and some theory-based questions. Okay, I mean the assembly, the first half on the MIPS and assembly, that will be mostly in the first few MCQ questions, right? And after that, the rest will be on the second half. You wouldn't be required to draw anything. Okay, so it'll be more on the just analyzing the code, okay, to answer some questions. Okay, so the majority of the marks is on the second half. Okay, for MCQ wise, I think it's about the first half is about roughly around 30%. Okay, the rest of the 70% will be on the second half of the content. I would say it is doable. Okay, I wouldn't say it's hard or easy. I would say that as long as if you are already confident based on what you've done for your assignments, then I think you shouldn't have any issue. Okay, and even the theory part, I think since it's open book, you don't really have to memorize anything, correct? As long as you know where to find the information, correct? So your material that you bring in, you just need to make sure it is, I would say, organized in a way that is easy for you, correct? If you just dump all your papers there, then you try to go through at that point of time, I think it will be very difficult, correct? But if you organize it a bit, then I think it will be easier for you, correct? Provided you know where to find it. Yeah, the first half is all the MCQ questions. The second half is the rest of the structured questions like what we went through today. Let me see, code analysis and some theory part. Am I excited for face-to-face classes? I think face-to-face classes are, of course, nicer, but I also understand that part-time students like for yourself is quite tough, right? Especially when you come after work. After students come all the way there and then they end up falling asleep, because you're so tired. Yeah, so I think that is a challenging part. But I guess I guess we are moving towards that already now, the face-to-face. So we just have to be prepared for that. Okay, any common mistake past year final? I would say not so. Generally, most students do quite okay, in the final. So I don't think there's anything major to sort. I mean, I think I said this before in the beginning. Okay, the only students who have failed this module are students who really, I would say, sort of gave up along the way for some reason. Okay, that means they never submit assignments or didn't show up for the exam or something like that. Okay, other than that, those who have been submitting assignments, who come for the exam, all have passed. Okay, so as long as you do, I think your part, you will definitely pass. And of course, if you've done better, then you get a better grade. Correct. car bike subsidy or this kind of things, I don't think so. You mean parking, is it? To park your car or bike, is it? Yeah, I'm not very sure, but yeah, I think the parking rate is different, right? Different car parks. If you park in SOC car park, it's very expensive if you don't have season. But if you park further down, besides at the foot of the arts canteen there, then that is a lot cheaper. But you need to walk up after that, you know. So yeah, so if you don't have season parking, when you want to walk around park, you probably have to look around and see the different parking rates. Okay, when you come for the exam, if you are driving or riding, you can't park at the MPSH, the main car park there. I mean, I think you can, but probably there are only very few lots available because most of them are reserved for the staff and the invigilators and things like that. Okay, so you probably want to take note of that and think of where else to park. Okay, so thank you. I'll see you all. Bye.